Okay, now we're going to talk about what happens if you have multiple measurements, each with uncertainties, and you're trying to work out something using all of them. And this is a bit more complicated, particularly philosophically. So for example, let's say you've got 5 different measurements, A, B, C, D, and E, and they're all uncertain, and you want to know what R is, which is just A plus B plus C plus D plus E. It could be, for example, you're going to put 5 bricks on top of each other, and you measure the height of each brick, each with an uncertainty, and you want to know how high the entire pile is. Now you might think that you just add up the uncertainties. So if each of these has an uncertainty of 1 millimeter, you might think the total uncertainty would be 5 millimeters. Each one's uncertain by 1, you're adding them all up. Now that's kind of right, but mostly wrong. Now, let's say you wanted to work out like the worst case scenario. What's the biggest the pile of bricks could be, or the smallest it could possibly be? It could be that every measurement you make was too high, in which case the final result might be 5 times the uncertainty higher. So if each measurement is uncertain by 1 millimeter and if everyone was one too high, the overall pile might be 5 millimeters too high. In that case, you have just added it all up. But if each measurement is independent, it's just as likely that each measurement could be too high or too low. So it's actually, in terms of probability, quite unlikely that all 5 measurements would be too high, just like it's quite unlikely that all 5 measurements could be too low. It's possible, it's just not very likely. On average, you might expect like 2 or 3 to be too high, 2 maybe to be too low, and so it's going to partially cancel out. So if you want to know the worst case, how tall could this pile possibly be, how small could this pile possibly be, then sure, add up the uncertainties. If you want the typical uncertainty, on average, how far off will the height of this pile be from what we expect because of the measurement errors, then you've got to factor in the fact that sometimes the number is going to be too high, sometimes the numbers are going to be too low, and that partially cancels the uncertainties out. So it's the difference between the worst case uncertainty and the typical uncertainty. Now in physics, we virtually always use the typical uncertainty. The reason is that very often you might not just have 5 uncertain variables, but like 10 to the 23 uncertain variables, and the odds of them all lining up one way would be incredibly small. For example, if you're measuring the voltage in a circuit, that will randomly vary because of the random thermal vibrations of the atoms, and each atom could be moving left or could be moving right, which could knock an electron one way or the other, so it could give you a bigger or a smaller voltage. This is what gives you like static on radio and TV sets. It's very unlikely that all 10 to the 23 atoms will be going the same way at the same time. So if you use that as your uncertainty, you're going to get a number that's of no practical use because it will never ever happen in the real world. So it's actually an officially defined standard is that we use the typical uncertainty. What's a typical, how far off it'll be, not the worst case scenario. Now to calculate this, you need to worry about the concept of independent uncertainties. Are your different measurements independent? Now we've said that the measurement, for example, of each brick could be too high or could be too low. Now that may apply sometimes, but if, for example, you're measuring them all with the same ruler and your ruler is dud, then if one's low, they're probably all going to be low because the ruler is the wrong length. If, on the other hand, it's just the ruler is accurate, but you're just not able to see exactly what the length is, that's a random uncertainty. It could go up or it could go down. So it's really important to think, are my uncertainties random? If one number is high or low, could the other one also be high or low? Or are they correlated? If one's high, they're probably all high. Generally speaking, for example, let's say you're measuring lots of things with a stopwatch. It's always hard to measure things on a stopwatch because there's a human reaction time. You see the event and then you press the button, but you're always going to be late by the human reaction time. So that's, again, if you're measuring, for example, lots of times using a stopwatch, they're all going to be late. So that's not an independent uncertainty. They're all going to be the same way, most likely. So that's what's called a systematic uncertainty. It always goes the same way. Now the maths I'm going to show you here for combining uncertainties only works if the uncertainties are random. That if one is high, it's just as likely the other one will be low. If it's systematic, like using a dud ruler or using a stopwatch, this doesn't apply. You should not use it. But anyway, here are the equations. There's one for addition and one for multiplication, but the addition one actually also works for subtraction, and the multiplication one also works for division. So that makes it easy. You don't have to remember a separate addition and subtraction. It's the same equation for both. When you're adding uncertain numbers or subtracting them or any combination of these things, what the answer is, you add the uncertainties in quadrature. What does quadrature mean? What it means is a bit like Pythagoras' theorem. You square all the uncertainties, add them together, and then take the square root. And that applies whether you're adding or subtracting things off. It's a bit similar for multiplication and division. Once again, you're adding in quadrature, but now you're adding the fractional uncertainties in quadrature. So what you do is you divide each uncertainty by the value, so sigma A over A, sigma B over B, sigma C over C. Take all these ratios, square them, add them up, take the square root, and that gives you the fractional uncertainty in your answer. So, let's do an example. Let's imagine you want to work out the length of a piece of string. How long is a piece of string? Now you might measure the position of the top of the string against the ruler. Let's say it's 12 plus or minus 0.5 millimeters. And you measure the position of the bottom of the string against the same ruler as 94 plus or minus 0.5 millimeters. So what is the length of the string? Now we're going to assume that you've not got a dud ruler, you're not making the same parallax error on both sides, that you're actually making a good job of measuring it with a good ruler, so the uncertainty in one is actually independent of the uncertainty of the other. So you've got a half a millimeter uncertainty, half the smallest measuring interval at both sides. So the length is subtraction, it's just the bottom minus the top, which is 94 minus 12, 82 millimeters long. What's the uncertainty? Well, this is subtraction, so we use the adding in quadrature equation. So we take the two uncertainties, should be a plus there, square them, add them together, so 0.5 squared plus 0.5 squared, add them together, and then take the square root, and that comes out as 0.71. So the length should be 82 plus or minus 0.7 millimeters, playing the usual trick of just quoting it to one significant figure. And that's how you deal with multiple uncertainties. You're adding, subtracting, multiplying, or dividing.